right, let's do a sound check and see if I can hear myself. Audio is looking good. What about video? Do I see my hand over there? Yes, I do. Okay, perfect. Then we are ready to get going. So, sorry about last week. I wasn't feeling well. I thought I could push through, and then by the time it was time to start streaming, I just didn't feel good to go. So, figured I would postpone it by a day or two, and that didn't end up happening, and yeah, here we are. So, this is to make up for last week's session, and we still, as of now, have a session scheduled for the usual Sunday. I say the usual Sunday. I think we've skipped, the past 3 out of 5 Sundays. But yeah, I have tomorrow scheduled. We've got today. And then I think I also have one. I didn't post it publicly yet, but I've put it on the calendar, on my calendar for Wednesday, I think. Oh, hi. Is this on Twitch or just on YouTube? Right now I'm doing this just on YouTube. The Twitch for now is more focused on my gaming stuff. I mean, I started off Twitch with a mix of both, but they don't really have a proper streaming category for, educational stuff. So, I don't know. I'm enjoying the YouTube streaming experience more than the one with Twitch, just because I have more tools available to me. I think Twitch has those tools too, but you have to be like an affiliate partner or something, and I'm not interested in that, so. Good question. Now, where was I? Right, so schedule, we've got one for today. Should be good to go tomorrow unless the unexpected happens. And I think I'm looking at Wednesday and possibly Thursday for some extra sessions to squeeze in, just so we can get the course done a little bit sooner, so that we can have time for review and stuff if needed, or just so I can free up time to work on other stuff. That's also a possibility. Now then, was there anything else in terms of announcements before we get started? I don't think so, but if I remember later, then I will bring it up. So let's start off with the 2 questions that I left you guys with last time. Last time I left you guys with 2 questions. Oh, and also I did take another look at this one question over here with the glancing collision with the 2 billiard balls of equal mass. And I found if you just do the conservation of energy equation, you realize that, You realize that V1 final squared and V2 final squared add up to V1 initial squared if you just do conservation of energy here. If you just do 1/2 m, actually I think I have it written here, right? I think I have it written over here. We can just rewrite it. Let me do it in a different color so that it doesn't blend in with all that other stuff. So if I did 1/2 m V1 initial squared plus, 0 is the initial kinetic energy of that second ball, then that will be equal to, since this is an elastic collision, the total kinetic energy should be the same after collision. So 1/2 m V1 final squared plus 1/2 m V2 final squared. Since all the masses are m, since the 2 objects have the same mass, the 1/2 m cancels out everywhere. and you end up with v1 final squared plus v2 final squared equals v1 initial squared. That tells you that v1 final and v2 final are the two shorter legs of a right triangle, with v1 initial being the hypotenuse of that right triangle. That tells you that these two deflection angles have to add up to 90 degrees. So that was one thing that came up last time that I didn't really have an immediate answer for. And then the other thing was this over here. I came up with this equation and didn't really see anything in it, but after looking at it again, I realized this is just the law of cosines. This is just the law of cosines, right? You've got a squared plus b squared minus 2ab cosine of the angle between them equals c squared. So yeah, that doesn't really do much for us here. It's this energy equation that really tells us that the sum of these angles is supposed to be 90 degrees. Oh, and I forgot to unplug these headphones. Let me put these away real quick. Otherwise my ears are going to start hurting. Okay, now the headphones are put away. I knew I was forgetting something. Lost my train of thought. What were we talking about? So, yeah, the important thing here is that 90-degree angle is a direct consequence of both of the masses of those two billiard balls being the same. Because if these masses didn't cancel out here, then we wouldn't have that v1 final squared plus v2 final squared equals v1 initial squared. We would have something else. Depending on the ratio of the masses, you would get some other triangle, which definitely wouldn't be a right triangle. So it only works if the collision is elastic and if the collision is between two objects of the same mass, and if one of the objects is initially at rest. So yeah, that was an interesting discovery. But now let's go ahead and look at the problems that I left you with. Let me actually open them in the books. Let me start with that first one. Let's see. Where are you? Should be somewhere around here. Okay, and it says... Wait a minute, where did it go? Ah, there it is. It says a 45-kilogram girl is standing on a 150-kilogram plank. The plank is originally at rest and is free to slide on a frozen lake, which is a flat, frictionless surface. The girl begins to walk along the plank at a constant velocity of 1.5 meters per second to the right, relative to the plank. What is her velocity relative to the surface of the ice? And what is the velocity of the plank relative to the surface of the ice? So just find the two actual velocities relative to the ground, a reference frame that we typically prefer to use. Let's go ahead and start this on a new sheet. Okay, so we have a 45-kilogram girl. The velocity of the girl relative to the plank is 1.5 meters per second. And then the plank was it 150? Yeah, 150 kilograms for the plank. $150 kilograms for the plank, and then the plank sits on top of the surface of some ice with negligible friction. Okay, so the only external forces that are left, we've got we're going to have a normal force and a gravitational force acting on the girl, which cancel out. And same thing with the plank. It's going to have two normal forces, one from the girl above and one from the ground below, and a gravitational force, and those are all going to cancel each other out. So the only remaining forces would be the force that the girl exerts on the plank, and in return, the force that the plank exerts back on the girl. Those are internal forces. Those are forces that parts of the system exert on each other. Our system being the girl plus the plank, of course. So net force external equals 0, which tells us that linear momentum is conserved. That tells us that linear momentum is conserved. Their initial momentum must equal their final momentum. Well, initially they're at rest. Initially they're both at rest. 0 plus 0 equals their final momentum is going to be 45 kilograms times velocity of the girl relative to the ground, or the ice, as they said, plus the mass of the plank, 150 kilograms times the velocity of the plank relative to the ice, which I would expect to be negative if we assume the girl steps to the right and we decide that right is going to be our positive direction. Then I would expect the plank to move left, which tells me then that the velocity of the girl relative to the ice has to be smaller in magnitude than 1.5. And that's because the velocity of the girl relative to the plank is going to be her velocity relative to the ice minus the plank's velocity relative to the ice. And this will actually be our second equation along with this one. Now that we have two equations and two unknowns, we can solve for the two unknowns. And I think we can just stop there, honestly. You guys know how to do the algebra at this point. The rest is just solving either using elimination or substitution. I would recommend substitution in this case. Just add v plank ice to both sides of that equation and then sub it in over here. And yeah, solve for the velocity of the plank and then solve for the velocity of the girl. You'll get something like, I don't know, for example, it might be something like 1.3 for the girl and negative 0.2 for the plank. 1.3 minus negative 0.2 would be 1.5. Something like that is what you're going to get. But yeah, I think we can leave the rest of this. Now let's take a look at that other problem with the cat and the sleds. Let's put this book aside and open this other one. Where is our cat problem? That's the wrong chapter. I think it might be here. Ah, found it. Okay, so it was two 22.7 ice sleds are placed a short distance apart, one directly behind the other as shown in the figure, which I drew before. It was this drawing. I just drew a cat's face because there wasn't enough room to draw a whole cat, at least not with my art skills. But yeah, we've got a pair of 22.7 kilogram sleds a short distance apart, one directly behind the other. A 3.63 kilogram cat standing on one sled jumps across to the other and immediately back to the first. Both jumps are made at a speed of 3.05 meters per second relative to the sled the cat is standing on when the jump is made. Find the final speeds of the two sleds. Okay, so these are going to be a pair of sequential collisions. So we're looking at a pair of sequential collisions here. Let's go ahead and figure out how to set this up. I'm just going to draw blocks for the sleds this time. So that's going to be 22.7 kilograms. And this is going to be another 22.7 kilograms. Should have drawn them the same size, but oh well. And then, of course, we have our cat. I don't know why I'm putting so much effort into this drawing. Hey, that's not too bad. I was expecting it to turn out worse. But hey, I made it work, kind of. Whatever, we'll give it some little eyes there. It's a grumpy cat. Anyway, this cat is 3.63 kilograms. And it makes two jumps. Each jump is at 3.05 meters per second relative to whatever sled it jumped off of. So it's going to make one jump, land on this sled. When it lands on this sled, everything starts at rest. So it's going to push off. This sled is going to start sliding backwards. I guess I might as well put a surface underneath everything. This first sled is going to start sliding backwards when the cat pushes off of it. The cat lands on this sled. When it lands, this second sled is going to move forward with the cat. The cat's going to turn around and jump off of the second sled back onto the first. And when that happens, well, the sled was already moving to the right after the cat landed, and when the cat pushes off of it, that's just going to push it to the right even more. It's going to get even faster as it moves to the right. And then the cat's going to land on this, and when it lands, the first sled is going to speed up to the left. So yeah, it's just a bunch of sequential collisions. Well, I guess in this case, two collisions that are occurring. And they're both going to be elastic collisions. So, other than the forces exerted by the cat and sleds on each other, do we have any other external forces? Normal forces and gravitational forces, but all of those cancel out very much like they did with this problem over here. So yeah, net force external is 0 here. We can use conservation of momentum. We'll do one collision at a time. So, we'll start with, can I put, well, there's no reason I can't put all three sleds into the same equation, but I think I would rather deal with two objects at a time. So initially everything is at rest. So 0 plus 0 plus another 0 if you want to put all three. You know what? Yeah, let's try and do that. Let's see what happens. Plus another 0 for the second sled. And then afterwards we're going to have 22.7 times, I guess we'll call this V sled 1. V sled 1. What would I call this? I don't want to call it initial or final. I'm actually not sure. I'll call it v sled left 1. Yeah, that's what I'll do. V sled left 1 plus, for the cat is going to, oh, wait a minute. No, if I want to solve for the cat's speed in the air, I think I have to deal with them 2 at a time. I probably should have taken some time during the past week or 2 to actually think about this some more, or week and a half, whenever it was that we actually first stated this problem. I've always just done it the slow way, but I was thinking there might be a faster way to do it. Anyway, I'll just do 2 at a time, forget about the second sled for now. So the sled is going to be pushed back at some velocity, and the cat is going to be pushing itself forward at some other velocity. So 3.63 times v cat 1. Okay, so we also know that the relative velocity between them is 3.05. We know that v cat 1 minus v sled left 1 is equal to 3.05 meters per second. I'm using right as the positive direction again here. So if we go ahead and try to solve for, I guess I want to solve for v cat, then add v sled left 1 to both sides, v cat 1 equals 3.05 plus v sled left 1, and take this and plug it in over here, and we get 0 equals 22.7 v sled left 1 plus 3.63 times 3.05 plus v sled left 1. Okay, there's going to be a 3.63 v when I distribute. So 22.7 plus 3.63, that's going to be what? 24.33, if my math is right. 22.7 plus 3.63, 26.33. Why did I even say 24? What was I thinking? Well, that's why I double check my work. And then 3.63 times 3.05, whatever that is, I'm going to subtract it over to the left. So 3.63 times 3.05 is 11.0715. I'll keep it unrounded for now. So negative 11.0715. And we're left with 26.33 v on the right-hand side of the equation. Okay, that's going to be, if I divide by 26.33, that leaves me with 0.42, negative 0.42. So the sled begins sliding to the left at 0.42 meters per second. Which tells us the cat is moving how fast? 3.05 plus negative 0.42, 3.05 minus 0.42. The cat is moving at about 2.63 meters per second in this case. So v cat 1 equals 2.63 meters per second. Okay, so that is the cat's speed in the air before it lands on sled 2. Now, let's see what happens when it lands on sled 2. Can you go over banked turn stuff? I don't know if we're going to get to that today, probably tomorrow, but we'll see how far we get into circular motion today. We'll see, but I am betting on tomorrow. Now then, where were we? So, cat is now in the air and is about to land on this sled. So I'm only considering the cat and the right sled for this next equation. So we have 3.63 kilograms of cat times 2.63 plus the right sled is currently at 0 momentum. And then the cat lands, and it should be an inelastic collision. So their final speed, well, not final, but you know what I mean. Their speed after the cat lands should be the same. So it should be 3.63. I guess I'll call it V sled right 1 plus 22.7. V sled right 1. This is probably not the best naming convention for variables, but it's what I was able to come up with in the moment, so we'll live with it. Okay, so 3.63 times 2.63 is 9.5469. I'll leave that unrounded for now. 9.5469 equals 3.63 plus 22.7. We did that before. That's just going to be 26.33 again. And let's see how fast sled 1 starts moving after the cat lands. So that's going to be 26.33, or no, wait, 9.5469 rather, divided by 26.33. I was about to divide wrong. Maybe I should have canceled today's stream too. But the show must go on. So I'm getting 0.3625. I'll just round that to 0.36. So the sled right 1 is equal to 0.36 meters per second. Okay. So that's another useful value we now have. The cat kicks off of the sled on the right and jumps back onto the sled on the left. So let's see what happens there. So they are initially, so the sled is initially moving to the right. So we're going to have, let's see, 3.63, I guess we'll call this VCAT2, plus 22.7. Wait a minute. I feel like I messed something up here. Give me a second to think. No, VCAT2 is going to be in the second half of the equation. So actually, it's just going to be this sum again, which is the 9.5469. Okay, yeah. It's 3.63 times 0.36 plus 22.7 times 0.36, which is this 9.5469 number that we got before solving. So it'll be 9.5469 equals, the cat jumps off, now it's moving at 3.63 VCAT2, which I expect to be a negative since it's moving to the left, plus 22.7 v sled right. Now it's going to be a second velocity for the right sled. It's going to be a little more than 0.36. Well, maybe not a little, but definitely more. And then the other relationship we have is that the relative velocity is again 3.05. That is, well, since it's going to be to the left, I guess it would actually be negative 3.05 equals v cat 2 minus v sled right 2. Does that make sense? Yeah, because v cat 2 I'm expecting to be negative. I don't see any scenario where it's not, minus a positive that I expect for the right sled. Yeah, this works. Okay, so I guess I will do pretty much the same thing I did back here. Let's solve for v cat 2 again. Just add v sled right 2 to the left-hand side of the equation. So v sled right number 2 minus 3.05 equals v cat 2. Looks like I'm going to need another page for this problem. And then take that and plug it in. Take that and plug it in all the way over there. Let me switch colors. And let's see what we get. 9.5469 equals 3.63 distributed over v sled right 2 and negative 3.05 plus 22.7 v sled right 2. Let me wall that off so that we don't confuse ourselves with it. Okay, so we're going to get 3.63v plus 22.7v again, so that's going to be another 26.33v, and then 3.63 times negative 3.05. We did that before as well. That was what we did back here, and it gave us 11.0715. So yeah, we get to reuse some old math. That saves us a bit of time. 9.5469 equals 26.33 v sled right 2 minus 11.0715. I'm going to add this to the 9.5469. So 9.5469 plus 11.0715 is 20.6184, and I'm going to divide that by 26.33. Divide by 26.33, and I get 0.783. I'll just round it to 0.78. So v sled right 2 is going to be 0.78 meters per second, and that is the final speed for the sled on the right. Nothing changes its velocity after that point, at least as far as this problem is concerned. Okay, next up we have the velocity of the cat in the air, so just take this number and plug it back in here. 0.78 minus 3.05. 0.78 minus 3.05 gets me negative 2.72. So v cat 2 equals negative 2.27 meters per second. I expected it to be negative. So now we know that. Can I actually squeeze it onto this page? I think I just might. I think I just might be able to. What color do I want to use? Let's use pink for this. Something a little bit brighter. I'll do it over here. So now that I know this, we are just going to have one more inelastic collision. The cat's in the air, headed left, going to land on the left sled, which was already moving at, where was it? The left sled was already moving at negative 0.42. So we've got 22.7 kilograms times it was already moving at negative 0.42 plus the cat is 3.63 kilograms times it's moving at negative 2.27. And in the end, both the cat and sled are moving at the same final velocity. I'm going to call that v sled left 2. So 3.63 plus 22.7. Well, we've done that dozens of times. Well, maybe not literal dozens of times, but you know what I mean. We've done that several times. For this problem, it's 26.33 v sled left 2. And let's see what we get for this. 22.7 times negative 0.42 plus 3.63 times negative 2.27. I'm getting negative 17.77 is what I will round it to. Or actually, you know what? Let's not round. Let's just write it as is, negative 17.7741. We'll round at the final step. Does that number make sense? Let's see. About 3.5 times 2 is about 7-ish. And this is about half, so 7 and a little less than 11 should add up to about 17-ish. Okay, I believe it. And divide by 26.33 on both sides, and I get v sled left after the second jump is equal to negative 0.675. I'll just round it. You know what? No, I'll leave it unrounded. Or rather, I'll round to 3 decimals instead of 2. Negative 0.675 meters per second. All right, so I guess what was the question even asking for in the end? What was the final velocity of everything? It said, find the final speeds of the 2 sleds. Okay, so that would be 0.78 for the one on the right and 0.675 for the one on the left. It said final speeds, so it wants magnitude, so drop your negative signs once you're done calculating. And as I always say, just express direction in words. If you're worried that you're going to lose points for not indicating the direction, indicate the direction with words. Just say 0.675 to the left instead of negative 0.675. Okay, now we can talk about uniform circular motion. Let me take a quick look at our course plan and see what topics I want to hit for today. Defining, of course, that's what we usually start with. So we want to define uniform circular motion and talk about tangential velocity and what it is, centripetal acceleration and what it is, centripetal force and why it's not a force to be shown on a free body diagram, and banked curves. Actually, we might be able to reach banked curves today, so for the person who asked, we might actually do a problem or two there. But in the history of AP Physics, I've looked at a lot of the old AP Physics exams, and I only found one AP Physics free response question on banked curves from like the 1990s, I'm pretty sure it was. Still, I mean, you never know when they might wake up and realize, hey, we haven't done a banked curve free response question since the 1990s. Maybe we should put that in this year's test. It would be a shame not to learn how banked curves work on the year that they finally decide to bring it back. So yeah, let's talk uniform circular motion. Let's talk uniform circular motion. That is the plan for today. The plan for today is to discuss uniform circular motion and the physics concepts related to it, the math, the misconceptions, the definitions, the everything. And we'll see if we can get through it all. If we don't, then that's what tomorrow is for. But if we do get through everything today, then tomorrow we can just get to work on gravitation, which is still going to involve uniform circular motion anyway, because we're going to be talking about things like the motion of planets and whatnot, and we're going to treat their orbits as being approximately circular. So without further ado, let's begin. Uniform circular motion. What's so uniform about it? An object is in uniform circular motion when it is moving at constant speed, not constant velocity, constant speed. Constant speed. When you see the word uniform, it means something has to be constant. In this case, it's constant speed circular motion. And of course, the other thing that defines uniform circular motion is the shape of the path. The shape of the path must be, a lot of people will say circular, but that's not entirely wrong. Must be a circle, or, this is the part that some students forget or just aren't taught explicitly, the shape of the path must be a circle or an arc of a circle, a segment of a circle. An arc of a circle. The shape of the path must be a circle or an arc of a circle. So if I have a car and it just turns around a corner, it's not moving in circles, but for that turn, if it makes the turn nice and smoothly, then that turn is an arc of a circle, so at least for a quarter of a circle you can be considered in uniform circular motion if that car moved with a constant speed. So it does not have to be a complete circle. If somebody, for example, swings on a vine and they somehow manage to do it at constant speed, the only vine scenarios I've seen recently anyway are situations like that one Tarzan problem we did in the work and energy example questions, where he was speeding up. So can't really claim uniform circular motion there, since the speed was changing. But maybe we'll come across something in the book later where you can have somebody swinging on a vine with constant speed. Who knows? So shape of path must be a circle or an arc of a circle. Just making a quick turn, like turning a corner, that's still uniform circular motion. You do not have to go in full circles. So, what are the requirements for uniform circular motion to happen? Well, if an object is moving with some sort of velocity, let's say a car again, and a car is moving with some velocity like this, in order for it to turn, you need to accelerate it. You need to change the direction of the velocity. So we need to change the velocity's direction, and because we want the speed to be constant, we need the magnitude of the velocity to be constant. So we need to apply an acceleration to this vehicle in such a way that there is a change in direction, but no change in magnitude. Well, we kind of talked about this one time when discussing, I believe it was projectile motion, where we said the only way to apply an acceleration that changes direction without magnitude is if that acceleration has no components parallel to the velocity. So the acceleration, whatever acceleration I apply, must be perpendicular to the velocity. And we actually did see that in projectile motion. We had, for example, when an object is at the peak of its trajectory. If I just throw an object from here, it moves at the peak of its trajectory, it's moving straight to the right, and the force of gravity acting on it, its acceleration, is still straight down. That just means for that next split second, it is, I guess, in very, very temporary uniform circular motion where it's just turning. It's just turning without speeding up or slowing down, but only for a very brief split second. In order to not curve like a parabola, right? This would be a parabola shape, not a circle. In order to not do that, the angle between the acceleration and the velocity needs to stay at 90 degrees. The problem with projectile motion, I mean, it's not really a problem, but the reason projectile motion isn't uniform circular motion is because when the direction of the object changes to like this, after a little bit of time, the force of gravity, the acceleration, is still straight down, and now it's going to have a component. If you broke it down into a component that's perpendicular and a component that's parallel to the velocity, then you would have something like this. Now it has a parallel component to the velocity, and that's going to affect the magnitude, so you no longer have that constant speed. Though that perpendicular component existing does mean that the object is still turning. So what we really need, in addition to an acceleration that's perpendicular to the velocity, is an acceleration that turns with the velocity so that it stays perpendicular to it, so that when this car turns, say, by the time it turns like this, and its velocity is now in this direction, we want its acceleration to have turned with it the whole time, so that the acceleration remains perpendicular to it at a 90-degree angle. Only if you have a force or combination of forces acting on the car in such a way that they turn with the car moment to moment to moment, only if you can get your forces to behave in that way will the car successfully be able to turn. Otherwise, in the absence of such forces, the car is just going to move straight, or if the forces only act, if your net force is only acting to the right here, then what will happen is it'll turn initially, but it won't turn in a circle. It'll just be basically like a sideways projectile. It'll end up turning like this. not in a circular path. So you need your forces to add up on the object in such a way that the net force, and therefore the acceleration, are perpendicular and stay perpendicular to the velocity of the object at all times during which the object is actually moving on its circular path. I guess what I'm trying to say is, if you see an object that's moving on a circular path, or at least a segment of a circular path, then that tells you that by some miracle, the forces already did that, and your job is to kind of work backwards and figure out how the forces combined in order to cause that to happen. This point is going to be brought up again later when we talk about centripetal force. But anyway, let's go ahead and define this acceleration. You need to have a certain amount of acceleration. The faster this vehicle is moving, the greater this perpendicular acceleration needs to be in order to successfully turn. With no acceleration, the object is just going to continue moving straight. With acceleration that's in a constant direction, the object is just going to curve. And if the acceleration does turn with it, if the acceleration does change direction with the object's velocity, you still have one more problem, which is the magnitude of that acceleration has to be sufficient. If it's insufficient, then the object will move pretty far ahead along its initial path before it turns. It won't turn fast enough to actually make a circular path. It'll probably actually swerve off like this and will look similar to what we get from projectile motion. So acceleration too low, and you're going to end up with one of these paths, which isn't exactly a circle, it's a little bit too wide. If the acceleration is too high, on the other hand, you're going to get these really tight turns that aren't circular either. So you need to find an acceleration of just the right magnitude. Let me do this in a different color. You need to find an acceleration of just the right magnitude to get your circular path. And I guess that's not a very good circle, but it's the best I've got for now. The magnitude of the acceleration needs to be sufficient. And what are the conditions that require more or less acceleration? What are the factors that I need to take into account to figure out how much acceleration I need? Well, think about if you're running straight ahead and you suddenly want to turn. Say you're, running along the sidewalk and you're about to reach the corner of a street and you want to turn that corner. You tend to slow yourself down to make it easier for you to make that turn. Whether you're walking on a sidewalk, or for those of you who are old enough to drive, if you're driving and you're rounding a corner, you tend to slow yourself down. That's because higher speeds require higher acceleration to turn. So one of the factors affecting this acceleration is speed. One of the factors is speed. Higher speed requires higher turning acceleration, or what we officially call centripetal acceleration. Higher turning acceleration. The other thing is the size of the turn. It's much easier to make a wide turn than a very quick and sharp turn, right? Wide turns are easier than sharp turns. So the radius of the turn, whatever the radius of your circular path is, that is another factor. Greater turning radius requires less acceleration. Greater turning radius requires lower turning acceleration. And so we are left with an equation for this type of acceleration, what we call centripetal acceleration. Centripetal acceleration. We are left with an equation for it, which is A centripetal, A sub c, is equal to v squared over r, where r is the radius and v is what we call the tangential velocity. Now let's talk about those names. So why is it called centripetal acceleration? Well, if you look at the circle I drew, the object's velocity, the object that's turning, its velocity is always going to be on the rim, on the edge of whatever this circular path is. So it's going to be tangent to that circle. That's why we call it a tangential velocity. So sometimes you'll see this written as v sub t, which stands for v tangential. And if the acceleration is perpendicular to that, if the centripetal acceleration is going to be perpendicular to that, it's also going to be in the direction that the object is turning. So it's going to be inward towards the center of the circle, hence the name centripetal, center seeking. So v sub t is tangential velocity. And it's called so because its direction is going to be tangent to the circle or circular arc that the object is moving along. And the acceleration is called a centripetal acceleration because it's always going to point towards the center of that circular path. If you don't have something that's pulling you towards the center of your turn, then what's going to happen is you're going to swerve off, or maybe just continue moving straight. Okay, so that's the equation for centripetal acceleration, but maybe you don't believe me. It's not like I exactly proved it, so let's talk about proof. Let's talk about proving it. I'm going to draw another circle. And let's see if we can prove something here. So here's the center of a circle. And let me try and draw it somewhat carefully. Make it look like one of my better circles. There we go, that's a pretty good circle. Okay, let's say that I have this circular path, and let's say that I have an object that starts off over here, and let's say it moves to over here. And let's say that this object is in uniform circular motion so that its velocity is constant. Okay, so from here to here, we will have moved through some angle. I will just call it theta. And this object will have, let me use a different color for this. This object, its velocity will have changed from this to this. If I draw those velocities tail to tail, then they would look something like this. Actually, let me draw them a little bit bigger so that I can more clearly illustrate what I'm about to show. So these should be of equal length. So that's, I guess we could call it, well, we're just going to call both of them V. And so this was the first V, this is the second V, and then the line I can draw connecting them, if I draw another vector connecting the two, actually let me use orange instead of green. If I draw a third vector connecting the two, this will be a vector that's added on to that first V to make the second V. This will be our delta V. V plus delta V, just tail to tip addition, equals this other V. Okay, so I've basically made a triangle here. And come to think of it, if I connect the dots over here, that's another triangle with sides R and R equal sides on, for this side and this side, it's just an isosceles triangle. Same thing here, that's another isosceles triangle. What is this angle over here? Well, if this first V was perpendicular to this R, and this second V over here is perpendicular to this second R, then since it's an angle of theta from the first R to the second R, then the two velocities must have swung by the same amount, right? If I put, let's say I put these two pens together, let's say they're like this, they're perpendicular to each other, right? If I swing the pink pen by, say, 15 degrees, the black pen, if it's going to remain at 90 degrees to the pink one, must have also swung by the same amount of degrees, must have also swung by 15 degrees. So we can say that this angle over here is also theta. Okay, then that means that this pink triangle and this blue triangle are similar triangles. They're not identical, but they are proportional to each other. They are proportional to each other. So then I can do V over R. I can do V over R, right? The ratio of one of the long legs on this triangle to one of the long legs on this triangle is equal to, well, I could do the other V over R, but that's not really, a profound discovery. V over R equals V over R. Wow, I'm so surprised. Of course, that's not the interesting bit. The interesting bit is this, is equal to delta V, the short side of this triangle, over the short side of this triangle. What are we going to call the short side of this triangle? I'm going to call the short side of that triangle S for arc length. Now, you might be saying, wait a minute, this is a straight line. That's not an arc length. Of course it's not an arc length, but consider this. If I walk 1 meter right now on Earth, the Earth is technically curved, but how much of a difference does it actually make if I calculate the very, very, very tiny angle between my initial position, my final position, and the Earth's core when walking 1 meter? How far from 1 meter will the actual distance be? It'll be negligible, right? Well, that's kind of what we're arguing here. We're arguing for very, very tiny angles because these delta V's are being applied. So I've drawn a much bigger theta here than I probably should have, just because I needed the space to actually draw it in. But we're really talking about very, very tiny changes, very tiny moment-to-moment changes in the object's velocity as it turns. And for those really, really tiny ones, if I were to draw this pink triangle again, with the circle, the difference between this arc length and, I'll draw it in dark blue, and this just straight segment, the difference in length between them becomes more and more negligible. You can barely even see the gap over there. The difference becomes more and more negligible as this angle shrinks. So we're going to say that this arc length is just going to be this straight distance. We're going to say that this arc length is just going to be this straight distance. And for this distance, the way we're going to calculate it is we're going to say that it's just the speed times the time. We're just going to say that it's the speed times the time. Well, the speed is v, and the time, we'll just call that t. So we can say v over r is equal to delta v over v delta t, or just vt if you prefer. Actually, I think I prefer vt, but we'll keep it as a delta t. So if I multiply this v over to the left-hand side, then I get v squared over r equals delta v over delta t. Oh, delta v over delta t should look familiar. What's that? That's acceleration. Change in velocity over change in time. Specifically, it would be the centripetal acceleration in this case. And that would be the tangential velocity. So there you go, we've proven it. Centripetal acceleration is v tangential squared over r. Let's do a quick exercise with that before we move on to some more stuff, some more concepts relating to this discovery that we've made, whatever you want to call it. I'm not doing too good with words today. Maybe streaming this late wasn't such a good idea. It's one thing to stream games this late in the day where you don't have to think too hard, but physics might be another story. Then again, I am used to tutoring in the evenings, so I think I'll manage. There's this one really simple problem that I like to give students when starting this chapter. Where is it? Okay, found it. And we might be able to squeeze it into this empty space before we start up a new page. So it says, a certain light truck can go around a flat curve having a radius of 150 meters with a maximum speed of 32 meters per second. With what maximum speed can it go around a curve having a radius of 75 meters? So we have a light truck that can go around a flat curve having a radius of 150 meters. Yeah, not a very perfect circle, but we'll go with it. 150 meters. It can go around a flat curve with a radius of 150 meters with a maximum speed of 32 meters per second. V tangential equals 32 meters per second at most. After that, it starts to swerve off because there's not enough acceleration. The source of the acceleration here, I would assume, is friction between the tires and the road. And And yeah, if the road isn't rough enough, then that's the fastest you can go. After that, the road's not rough enough to keep you there. You'll start swerving. With what maximum speed can it go around a curve having a radius of 75 meters? So if we make a tighter turn like this, I don't think that's exactly half, but it'll have to do. If the radius becomes 75 meters under the same, under the same surface conditions for the road, you should end up having the same centripetal acceleration in both cases. So what is the maximum v tangential that we can handle in this scenario? Really easy question. Really, it's just plug numbers into the equation and see what you get. So we're going to do a centripetal equals 32 squared over 150. And whatever that centripetal acceleration is, it better equal this new v tangential squared. I guess I'll call it v2 squared over 75. And so I can multiply the 75 over, and that reduces with the 150 to 1/2. So 32 squared over 2. 32 squared over 2 equals v2 squared. 32 squared is 1,024. 1,024 over 2 is 512. Square root of 512, which is going to be, what, 16 square root of 2. I know these numbers because they're computer numbers. They're like disk drive sizes, right? 1,024 megabytes is a gigabyte. Yeah, that's 32 squared. 32 is 2 to the 5th power, and 1,024 is 2 to the 10th power. I know that because I studied computer science. Anyway, 32 squared over 2, and then if I square root that, 16 root 2, which is also what in decimals? About 22.63. V2 is about 22.63 meters per second. So cutting the radius in half did not actually cut the speed limit in half. Cutting the radius in half does not actually cut the speed limit in half here. That's because the centripetal acceleration is related to the square of the tangential speed. Just remember that, because that does throw a wrench in things. If your turning radius increases by a certain factor, your tangential velocity does not increase or decrease by that same factor. Just keep that in mind. Okay, so that's a quick example doing centripetal acceleration. I guess we can now talk about what creates centripetal acceleration, and this is going to be like the core of this chapter. This is going to be what makes or breaks the problems that you'll be solving for this chapter. Well, at least for the circular motion part of this chapter. Centripetal force. Now, this is something that a lot of students misunderstand. Centripetal force. Centripetal force is not a new kind of force. It's not, if you saw my force video where I listed the 7 forces that you will encounter in Physics 1. Actually, I guess 8. Now that Physics 1 also includes fluid mechanics, you'll also deal with the buoyant force, but I digress. The 7 forces in that one worksheet we did were applied force, gravitational force, static friction, kinetic friction, tension, normal force, and what am I missing? Spring force. Those were the 7 forces of AP Physics 1, plus buoyant force, as we will see in the last chapter for fluid mechanics. Centripetal force is not being added to that list. Centripetal force is not a new kind of force. Centripetal force is not something you draw on a force diagram. And the reason you don't draw centripetal force on a force diagram is the same reason that you don't draw your net force on a force diagram. If I have an object, with a force applied this way and a normal force this way and a gravitational force this way and some, let's say, kinetic friction this way, and overall the object accelerates to the right, then I would say the net force on this object is to the right. But do I draw my net force on this diagram? Do I do this? Have I ever done this? Nope. We don't draw the net force on our diagram. You're basically double counting the force. That's not good. The net force is already on the diagram. It's the sum of the forces that are already drawn there. Centripetal force is the same thing, and that's because centripetal force is the net force. Centripetal force is just a special case of the net force. Centripetal force, you want to think of it as a special case of the net force. Specifically, it is the case where forces add in such a way that the direction of their sum that is, the direction of the net force remains perpendicular to the object's motion. Remains perpendicular to the object's motion. Very, very important to understand this idea. Centripetal force is not some new kind of force that you can just draw on your force diagram. That is not what's going on. Something moving around in circles is not generating a centripetal force. You're mixing up cause and effect there. Centripetal force is the cause, uniform circular motion is the effect. If something is moving around in circles, that means whatever forces are acting on it, be they tension or friction or applied force or some combination of multiple forces, whatever forces are acting on the object, they just so happened to combine in such a way that the direction of their sum, the magnitude of their sum is constant, and the direction of their sum is changing in tandem with the motion of the object, turning with it remaining perpendicular to its velocity for the duration of that circular path or segment of a circular path. That's all that's going on. That is all that's going on. Kind of what I mentioned before, where if you see an object in circular motion, then that just tells you that the forces acting on it have to have assembled themselves in such a way that made it possible. You're just looking at the effect and working backwards, reverse engineering that to figure out the cause. Circular motion does not create centripetal force. It's centripetal force that creates circular motion. Okay, so the direction of the centripetal force should be the same as the direction of the centripetal acceleration. What about its magnitude? Well, the more centripetal acceleration you need, the more centripetal force you would need. The faster an object moves and the sharper the turn, the more centripetal force you would need. So it would make sense then that centripetal force, what I'm going to call net force centripetal, some people don't use the net symbol, and I think that contributes to the confusion on this. But net force centripetal is simply equal to mass times acceleration centripetal. That's all it is. So centripetal force is not a new kind of force, it's just a new possible outcome you can get after summing the forces on an object. After summing the forces on an object, if that net force happens to be in the direction that the object is already moving, or if the object started from rest, then the object will just move in a straight line. If you sum the forces on an object and it turns out that the direction of the net force is not the same as the direction the object is moving, not parallel to it, let's say you have a projectile, for example, at the height of its trajectory, and it's moving to the right while the net force on it is straight down, well, then that's going to move in an arc because the net force is perpendicular at the start, but it doesn't stay that way for very long, and you just get a parabolic path. And if the net force on an object does turn as the object turns, then what you get is circular motion. So it's just a new behavior that can result from your net force if it just so happens to have the property that it turns and changes direction with the object. So a really simple equation, it's just Newton's second law, really. We're just applying it to the centripetal case of net force. Okay, I think we should just look at some problems and try to piece together this concept a little bit more through that. So let me find some problems that we can do. The problem with this chapter in my book is that it kind of mixes some rotational kinematics in here, and I like to put that in the rotational dynamics chapter. Oh, here's a good one. So it says an air puck of mass 0.25 kilograms. Let me draw the illustration first. Don't want to use that color. We've already used it too much. How about orange? Okay, so they have a table. They've drawn a table, and this is more of a 3D picture. So they've drawn a table. And on top of this table, they have this disc, what they called a puck. I guess, yeah, there's the fourth leg of that table. So they've drawn this little puck, this little cylindrical piece, and then there's a hole in the table. There's a hole in the table, and through that hole there is a string. And let me do that in a darker color. So there's a string, or cord, or rope, whatever you want to call it. And it also goes under the table. And under the table, you see that this string is connected to a block. So it says the air puck of mass 0.25 kilograms, so this thing has a mass m puck is equal to 0.25 kilograms, is tied to a string and allowed to revolve in a circle of radius 1 meter. So it turns in a circle with a radius of 1 meter. So here is the shape of its path. It just circles around and around on this table in a radius of 1 meter. R equals 1 meter. On a frictionless horizontal table, so there's no friction, the other end of the string passes through a hole in the center of the table, and a mass of 1 kilogram is tied to it. So this thing is 1 kilogram. M block equals 1 full kilogram. The suspended mass remains in equilibrium while the puck on the tabletop revolves. Suspended mass remains in equilibrium. That means that the net force on the block has to be 0. Part A, what is the tension in the string? What's the force of tension? Part B, what is the horizontal force acting on the puck? Horizontal force on puck. And part C, what is the speed of the puck? Part C, V, I guess we'll call it V tangential. What is the speed of the puck? All right, so first, the tension in the string. Well, for the block, we can draw its force diagram. I keep on grabbing this pen. Let's try red. So for the block, I can do the force acting up on it is the force of tension, and the force acting down on it is the force of gravity, and I see no other forces over here. It's not touching any springs, it's not in contact with a surface, so there's no friction that we need to consider. Yeah, it's just tension and gravitational force, and it's in equilibrium. The net force has to be 0 in the x direction. That's easy because there are no forces in the x direction. Net force has to be 0 in the y direction. That means force of tension minus force of gravity must be 0, or the other way around if you prefer, gravity minus tension being 0. It all leads to the same result. The magnitude of the tension force must equal the magnitude of the gravitational force, must equal mg. Specifically here, m block times g, so equals 1 kilogram times 9.8. 9.8 newtons. Force of tension equals 9.8 newtons. All right. What is the horizontal force on the puck? So I'm going to draw a second diagram of the puck, and this time I'm going to look at it sideways. This time I'm going to look at it from the perspective of somebody who's looking at the table from the side, somebody who's looking at the table, say, from this direction. Here's another giant eyeball of physics for you. So somebody looking at it just from the edge, just from the side of the table, what do they see? They see the puck like this, on top of the table and connected to a string. Let's say the string it happens to be on this side when they look. There's going to be a normal force acting on it. There's going to be a gravitational force acting on it. And there's going to be a tension force acting on it. And they said that the surface of the table was frictionless, so it'll just be those three forces. Normal force and gravitational force on the puck will cancel out, and that just leaves the tension force. So what's the horizontal force on the puck? It's the tension force, which is 9.8, because that's what it is on the other end of that rope. So horizontal force on the puck is 9.8 newtons. It's the tension force. It's the same tension force that acts on the block, same magnitude. And what is V tangential of the puck? Well, let's see. So we see that the net force on the puck is this tension force. Net force on the puck is equal to the force of tension, is equal to 9.8. But the other thing that you might notice is that this net force is a centripetal force. And how do we know that? Well, because the direction of this tension force is constantly changing. As the puck swings, so does the string, and the tension force is always going to be parallel to the string. So as the string and puck turn, so does the tension force. Here's our first example of this type of behavior. A net force that's changing direction as the object moves, and changing direction in such a way that it remains perpendicular to the object's direction of motion. This net force isn't just any net force, it's a centripetal one. That means it's equal to the mass of the turning object, 0.25 kilograms for the puck, times the centripetal acceleration, V tangential squared over r. V tangential squared over a radius of 1 meter. It has to be. If it wasn't, then this motion wouldn't even be happening in the first place. Okay, so how fast is this puck moving? If we go ahead and plug in our numbers, I guess we'll just do 9.8 divided by 9.8 divided by 0.25. 9.8 divided by 0.25, we get 39.2. If I take the square root of that, V tangential is about 6.26. So I'm getting V tangential is about 6.26 meters per second. If the puck were to move any slower than that, then the net force over here would be more than sufficient to provide the centripetal force, and the leftover force that's not being used on making the puck turn would instead be used on drawing the puck in, and that would cause the radius of this circle to shorten as more and more string gets pulled in. And maybe eventually it would get to a point where the radius is small enough that in order to maintain its speed, the magnitude of the centripetal force will have increased. And by that point, once you reach that point, then it will remain in circular motion. But that's not the problem they gave us. We might get a problem like that in a future chapter, actually, in the next chapter, rotational dynamics, we might get a problem like that, which asks us, what happens if the object is moving slower than what the net force allows for? Because I think we might need some angular momentum concepts in order to solve such a problem. Either that or it's just been too long of a day for me and I'm not thinking straight. I would probably place more of my bets on the latter. And that solves the third part of this, so we're done. 6.26 meters per second. Okay, let's take a look and see if we can find another one. So in this case, our centripetal force was supplied solely by one force, tension. But let's see if we can find one where a combination of forces is required. Oh, here's one. This is a classic. So it says a roller coaster vehicle has a mass of 500 kilograms when fully loaded with passengers. If the vehicle has a speed of 20 meters per second at point A, they have this illustration. So they have a roller coaster. I'm just going to draw the path. And I guess I'll draw a block to represent the roller coaster itself. So they have this. Notice, not complete circles. Here we're just looking at segments of circles. Actually, let me draw that a little bit lower, something like that. Scratch that. Okay, so this is what they called point A. This is what they called point B. So it says roller coaster has a mass of 500 kilograms when fully loaded with passengers. Here it is. 500 kilograms. Okay, I guess I drew that a little too big, but it'll have to do. If the vehicle has a speed of 20 meters per second at point A, what is the force of the track on the vehicle at this point? And then second question, what is the maximum speed the vehicle can have at point B in order for gravity to hold it on the track? What color do I want to use here? How about you? Okay, so at point A, VA, I'm going to call it, is 20 meters per second. And they're asking for the force that the track exerts on the vehicle at that point. When the vehicle is at this point, when your 500 kilogram mass is at point A, forces acting on it are normal force upward and gravitational force downward. And it is on a part of a circular path. It's moving through a segment of a circle, and if it wants to move through that segment at a constant speed, then it needs to turn up, so it needs a sufficient centripetal acceleration supplied by a sufficient centripetal force to allow that to happen. That means the net force on this object needs to be in what direction, first of all? We'll worry about magnitude in a minute, but what about the direction? Well, if the circle that this segment is a part of is centered up here, then the net force needs to be up. It needs to be towards the center. So if the only forces acting on this object are normal force and gravitational force, then that means I need my normal force to be greater than my gravitational force. That's the only way that this would work. I need to have some net force directed up. So I need my upward forces to be greater than my downward forces. I need this combination of forces to result in an upward force of sufficient magnitude to make this possible. So normal force minus gravitational force minus 500 times 9.8. That's going to be my net force. It needs to equal the mass times the centripetal acceleration, v tangential squared, in this case 20 squared, over the radius of the turn, and the radius is shown in their diagram to be 10 meters. I forgot to write that here. That's 10 meters, and come to think of it, I might as well write this one since we'll need it for the next part. This one is 15 meters. Okay, so 20 squared over a radius of 10 meters. So 500 times 20 squared over 10, so 500 times 400 over 10, that's 500 times 40. And then add 500 times 9.8, so that's going to be 500 times 49.8 is 24,900. I believe it. 24,900 newtons of normal force are required. That's the force that the track would exert on the roller coaster car at that bottom point. What about other points, like here or here? Well, in that case, the normal force is going to be at an angle, and you're going to want its upward component to be 500 times 20 squared over 10, plus mg, of course, because it also needs to cancel gravity. And its horizontal component, well, I would hope it cancels with friction or something. Otherwise, if you're left with a horizontal component here, that just means you're going to experience some deceleration. We'll look at a problem where the normal force is at an angle in a bit. So don't worry too much about that right now, but just quick food for thought. Anyway, second part of this was, what is the maximum speed the vehicle can have at point B in order for gravity to hold it on the track? What's the fastest you can be at point B? There's a limit to how much centripetal acceleration you can have because there's a limit to how much centripetal force you can have. So once we figure out what's the maximum magnitude of centripetal force we can have at this point, we can then figure out what's the fastest that centripetal force will allow us to go, and that'll be our answer. So let's go ahead and do that. So up here, the diagram is going to be pretty much the same. There's going to be normal force, and there's going to be gravitational force. And this time, the center is straight down. So in order for your net force to act as a centripetal force, your net force has to point straight down, at least for that moment. So that means the gravitational force needs to win over the normal force. Our net force centripetal, in this case I'll do gravitational minus normal. Force gravitational minus force normal equals mass times v tangential squared over r. Okay, we are trying to maximize v tangential. We can't change the mass, we can't change the radius, we can't change the weight, we can't change what planet we're on. It's going to be 500 times 9.8 no matter what we do. So the maximum V tangential occurs when this side of the equation is the highest it can go. And since we can't change the force of gravity, we want the amount subtracted from it to be as little as possible. What's the lowest possible normal force we can have? None at all. If we have zero normal force, that is our best case scenario. Well, I wouldn't call it a best case scenario. I would say that it's actually a pretty dangerous case to be in when gravity is the only thing keeping you down. And you're just on the edge of what gravity can do to keep you grounded. I wouldn't call that a best case scenario per se, but in terms of the goal of this problem, in terms of the goal of maximizing tangential speed, yes, this is the best case scenario for us because normal force cannot pull. We cannot have a normal force that acts downward. If we could, that would open up more possibilities, but yeah, maximum centripetal force in this case is when gravity doesn't have to fight the normal force at all. So that gives us mg equals mv tangential squared over r. The m's cancel. So you're just left with g equals v tangential squared over r. Multiply g by r, so 9.8 times 15, and take the square root. 9.8 times 15 is 147, and the square root of 147 is 7 square root of 3, but also, what else, calculator? 12.12. So I'm getting v tangential is 12.12 meters per second. Any faster than that, and the gravity is not enough to keep that roller coaster car on the tracks. And that means that if you go any faster than 12.12, this happens. No more circular motion. Hello, projectile motion. You, dear roller coaster rider, are the projectile. Enjoy the last few seconds of your life. Once you understand the rules of circular motion, you gain an appreciation for all the safeguards that need to be put in place in order for most amusement park rides to work. Or you get traumatized and never want to go to an amusement park ever again. Understanding uniform circular motion can save your amusement park from lawsuits. And can save you from, well, quite literally, a tragic death. Okay, let's have a look at another one. So this one is a Ferris wheel. And this will introduce us to a new concept that will become more useful when we look at gravitation, a new concept relating to circular motion. Actually, it relates to a bunch of different types of motion that can occur on a repeating basis, but we'll talk about those when we get to them. So it says we have a 40-kilogram child. Let me actually draw the Ferris wheel first. Okay, that'll have to do. So we have a 40-kilogram child takes a ride on a Ferris wheel that rotates 4 times each minute. This is known as period. Or, wait. Well, not quite, but we can use it to calculate period. So it's 4 rotations per minute. Or in other words, 1 rotation every 15 seconds. 15 seconds per rotation. That 15 seconds is what we call period, represented with a capital T. Period is 15 seconds. The time it takes for one repetition of some type of motion, in this case, one cycle around the Ferris wheel. This is called period. Also related is the inverse of period, 1 over period. The number of cycles that can occur per second, that's called frequency. You can also say it's got a frequency of 1/15th, and then the units for frequency are the hertz, Hz. You probably have heard the refresh rate on your computer monitor being described and measured in megahertz, millions of hertz, millions of, I guess, screen refreshes, screen flickers per second. Well, actually, wait, is it in megahertz? I don't even know. I don't pay attention to that stuff, but anyway, there you go. That is the unit for frequency, the hertz, which is also just a unit of 1 over seconds. 1 hertz is also just 1 over a second, or sometimes it's called seconds to the -1. You might see it written in any of those forms, but I prefer hertz. So yeah, one is seconds per cycle, the other is cycles per second, and cycles aren't really a unit, so you're just left with blank units over seconds. A per second, a hertz. Anyway, let me continue reading the problem. So, a 40-kilogram child takes a ride on a Ferris wheel that rotates 4 times each minute and has a diameter of 18 meters. Be careful about that. Diameter is 18 meters. That means the radius is 9 meters. Radius equals 9 meters. So part A, what is the centripetal acceleration of the child? Part A, what is the centripetal acceleration? Part B, what force, magnitude, and direction does the seat exert on the child at the lowest point of the ride? The force of the seat would have to be the normal force. So B, normal force, lowest point. Part C, what force does the seat exert on the child at the highest point? So again, normal force, but this time when the child is at the highest point of the ride. And part D, what force does the seat exert on the child when the child is halfway between the top and bottom? And for all of these, it wants magnitude and direction. Force, normal. Where did it go? Halfway between the top and the bottom, halfway point. How are we doing on time? We're at the 2-hour mark. Okay, so at the top, at the bottom, and then at the halfway point we can pick either of these. Let's say this one. It doesn't really matter. So we need to figure out what the normal force acting on the child is in each of those cases. Okay, at the lowest point, normal force up, gravitational force down. And I would expect to have more normal force than gravitational force, because if this person is going to be in uniform circular motion, their net force needs to always be pointing towards the center of their circular path. So normal force must be greater than gravitational force to have a net force pointing up towards the center when you're at the bottom. When you're at the top, there's going to be a gravitational force downward and a normal force upward. This time I expect the normal force to be lower so that there's a net force down towards the center. The center is down when you're at the top. And over here, force of gravity is still straight down. And then the normal force is going to have to be at an angle. Well, actually, I guess it would be a combination of normal force and some other force, or I guess you could also have two normal forces. So one way you could visualize this is, here's the seat, and then here's the child sitting in their seat. And you could say a normal force is exerted upward by the bottom of the seat, while another normal force from the back of the seat is exerted on them that way. That's one way you could think about it. Or you could say instead the source of your horizontal force could be a friction force, a static friction force between the child and the bottom of the seat. In fact, that would be more likely when the Ferris wheel is on the exact opposite side, where the child doesn't have another back of the seat, in front of them to push them that other way. So it would have to be friction in that case. But either way, whether it's friction or a horizontal normal force, it's force exerted by the seat. So I guess we'll just call it force seat. I guess we'll just call it force seat overall. Either a combination of two normal forces or a combination of a normal force and a frictional force. But yeah, in this case, you have to have it at this sort of angle because you need two forces from the seat. You need one to cancel with the force of gravity because your net force has to be to the right at this point. So your vertical forces have to cancel out, and you still have to have some force to the right. Your net force can't be to the right if you don't have any forces to the right. So the seat has to be exerting something to the right in order for this to work. So let's go ahead and work all that out. What is the centripetal acceleration of the child? Well, if they do 4 rotations per minute, if the period is 15 seconds, let's see how we can work with that. So if you're in uniform circular motion, you're moving at a constant speed. For a constant speed, you can say distance is equal to your speed times your time. So in this case, if your time is 15 seconds, then your distance is 15 seconds for a single rotation. So your distance is 1 full rotation. That's the circumference of the circle. That's 2 pi r, which is 2 pi times radius is 9 meters. And that allows us to solve for v. So in general, you can say for circular motion v equals 2 pi r over the period. Not the most important equation to memorize. I know I'm always telling you guys to memorize equations. This one, not super important to memorize because, you kind of already have it. As long as you can remember distance is speed times time, you can piece this together. Remembering that distance is speed times time, and remembering that period is the time for 1 full cycle, and then realizing that 1 full cycle is a distance of 2 pi r. If you have all those pieces, you don't need to explicitly memorize this. In fact, I would advise against it. I think mastering that reasoning process and going through it really quickly is better for your understanding of physics overall. So yeah, one of those cases where I'm not telling you to memorize. Let me get a sip of water. Okay, now let's go ahead and solve for v. So it's 2 pi times 9 divided by 15. And I'm getting about 3.77 if I round it, 3.77 meters per second. That's going to be my tangential speed. So I'm getting v equals 3.77 meters per second, which then tells me what? Well, I can use that now to calculate my centripetal acceleration because it's just going to be v tangential squared over r. 3.77 squared over 9. So 3.77 squared over 9, that's going to be about 1.58. That's about 1.58 meters per second squared. So that's part A done. And of course we're going to use that for parts B, C, and D. So for part B, what's the normal force at the lowest point? How much centripetal force is needed in order for this Ferris wheel to work? Well, they said the mass of the child was 40 kilograms. I forgot to write that down here. Mass of the child was 40 kilograms. And we have, in this case, I want to do up minus down. Forces, I will always do for centripetal force. I will always try to do forces toward the center minus forces away from center. So toward the center is going to be my positive direction for these sorts of problems. So I'm going to do normal force minus mg equals m times a centripetal. Normal force equals mg plus m a centripetal. Normal force equals 40 kilograms times 9.8 plus 1.58. If I factor out the m from these two, that's why the 40 is outside there. So 9.8 plus 1.58 is 11.38, and multiply that by 40, and I get 455.2 newtons. So second answer is 455.2 newtons. For part C, at the highest point, so this was at the lowest point. Now let's take a look at the highest point. At the highest point, we've got mg minus normal force this time, down minus up, equals mass times centripetal acceleration. Add the normal force to the right, subtract mass times centripetal acceleration to the left. I get mg minus mac equals normal, equals force normal. So we get 40 times 9.8 minus 1.58 equals the normal force this time. 9.8 minus 1.58 is 8.22, and then that multiplied by 40 is 328.8. 328.8 newtons Okay, so that's 328.8 newtons of upward force. Not a lot of net force needed, it looks like. 40 times 1.58. Yeah, that's about like 6. Hold on, let me just multiply it and see. 40 times 1.58. That's 63.2 newtons of net force is really all that's needed here. Which makes sense given how slow a Ferris wheel moves. Okay, that's part C. Part D. For part D, I guess I called it normal force over here, but it's just the problem said the force of the seat. And it wanted magnitude and direction, so I think we're going to have to determine an angle here. So the force of the seat this time, let me switch to another color. What have I not used in a good bit? How about red? Actually, I think I'll use this one instead. This darker, I don't even know what to call it, burgundy color, brownish red. So we're gonna have the full force of the seat is this. It's going to have a component that is just going to cancel with the gravity because my net force has to be towards the center. It has to be towards the right, which means it can't have any vertical components at this point. And then whatever's left over here is the horizontal component. That's going to supply my centripetal force. So this is just going to be equal to mg, and then the horizontal component, we just calculated a minute ago that it was, what, 63.2? Yeah, that we need 63.2 newtons of net force. Mass times centripetal acceleration is 63.2 newtons. So net force in the x direction has to be 63.2 newtons. So that means this, the only force in the horizontal direction at this point, has to be 63.2 newtons. And then this has to be 40 times 9.8, 392. Since the force of gravity is 392 on this child, this component of the seat's force must also be 392. And with that, we can now just do Pythagorean theorem to figure out what the magnitude of the force of the seat should be. It will be 392 squared plus 63.2 squared, square root, and I get 397.06. I get 397.06 newtons at what angle? Let's go ahead and look. So I'm gonna find this angle, which means I need the vertical over the horizontal, and I'm gonna use inverse tangent for this. So inverse tangent of 392 over 63.2 is 80.84 degrees. I'll say 80.8. So it's going to be at 80.8 degrees, at 80.8 degrees above horizontal direction. And that is part D. If an object is going to move in circular motion, in uniform circular motion, then the forces acting on the object must add up in such a way that their total is towards the center of that circular path. And if it's just a part of a circular path, you draw the whole circle anyway and figure out where the center of that circle would be, and the net force would have to be towards that center. All right, hopefully those examples were enough to kind of drive the point home. Now I suppose we can look at the case of driving around in circles, and I think we can actually wrap up with that. Let me think, is there anything else I'm missing? Well, there is. No, I'll leave that problem as homework. Yeah, let's do a banked curve problem. Let's talk about banked curves, and we will wrap up with that. Banked curves, and I'm not going to fit this all on this page, but just a quick little discussion. What does it mean for curves on the road to be banked? Well, if you've been in a vehicle on a highway recently, then you've probably noticed that when the highway curves, a lot of times the road is kind of tilted downward in the opposite direction to how the curve to the way that the curve of the highway is. I guess those words don't make much sense, but if, let's say you are inside this car. So here's, I guess, the windshield, and there's the driver who doesn't have their hands on the wheel. Quite dangerous, but we'll go with it. And then I guess there's like the lights of the car. And then you have the wheels. And this is the view of the road. Okay, it's not tilted this sharply, right? Usually it's not that steep, but you notice that the roads are kind of angled downwards when you're making, if I'm looking at this car from a helicopter, when this car is over here and driving down this way, you might notice that the road is tilted down this way. The road is tilted towards where the center is. Since the center is to the left of this vehicle, it's tilted down, the road is tilted down and to the left. Why is that? Well, that helps you get the centripetal force you need to turn at high speeds. That helps get you the centripetal force you need to help turn at high speeds, because it allows a little bit of the gravitational, well, actually no, the gravitational force would cancel out. It allows a little bit of the force of the road on the car. It allows a little bit of the normal force exerted by the road on the car. It allows a little bit of that. It allows a component of that to act towards the left. So you'll see that normal force component over here from the helicopter perspective. And that just gives you some more centripetal force. In addition to this normal force, you will still have the friction force. You will have the friction force, which is going to be down at an angle, and only a component of it will actually add to your centripetal force. But yeah, some combination of normal force and friction force will help you from, well, sliding up this way, right? The risk is that you might slide up in this direction. We don't want that, because that would mean, from the helicopter perspective, that means you're, moving out of the road this way, or maybe you're not even moving to the right necessarily here. Maybe you're just swerving like that and getting off the circular path, and that's not good. We don't need cars flying off the rails, flying off of highways, especially when they're driving at really high speeds. They're a danger to the driver and potentially other people that could be in the car's unexpected path. So we want cars to be able to go fast on the highway, but we also need to make sure that they can get the centripetal force they need to be able to go fast without swerving off the path. So that's why roads are banked. If the roads were not banked, if this was just a simple flat road, then the only thing you would have, if this was just a simple flat road, then here's that same car again. With the same reckless driver with their hands not on the wheel. And now, if this driver is turning to, I guess it would be their right, our left, the only thing that they have working for them now is the force of friction. The only thing they have working for them now is the force of friction. That's the only force that they can have in the necessary direction. The normal force is completely vertical, and it's all going to get wasted on canceling the force of gravity. And because friction can change depending on road conditions, right? You might have, for example, on a rainy day, the road is wet and the coefficient of friction is lowered, or maybe on a snowy day, it's really slippery and you can't get enough traction. Those are not good circumstances to be in. In that case, it's even less likely that you'll have enough friction. I mean, even on a good, warm, dry day, you saw back when we discussed friction, there aren't a lot of materials out there that have really high coefficients of friction. Most of them tend to be less than 1. But if you can change it so that some of the normal force contributes to your centripetal force, the normal force has a much, much higher limit depending on the strength of the material that the road is made of. I mean, when you think about it, what's easier to overcome? Just thinking about it intuitively, what do you think would be easier for you to overcome? The friction on a car, or the amount of force it takes to crush the material that the road is made of? I mean, if you see a lot of the potholes that exist around my area, you might have your disagreements with this, but I think it would be easier to push a car against the friction between it and the road than it would be to take a chunk of the asphalt that the road is made of and, try and crush it with my bare hands. I think I'd have an easier time pushing the car, as heavy as it may be. So I would argue that the normal force can supply much more force, even when you don't tilt the road by that much. It has the potential to supply a lot more force than friction could ever hope to. I mean, by definition, well, not by definition, but looking at most friction coefficients, the friction usually for most materials is going to be a fraction of what the normal force is. And usually a small one. I already used that side of the paper. So let's grab one more new sheet for the day. And let's try this problem. It says, an engineer wishes to design a curved exit ramp for a toll road in such a way that a car will not have to rely on friction to round the curve without skidding. He does so by banking the road in such a way that the force causing the centripetal acceleration will be supplied by the component of the normal force toward the center of the circular path. Show that for a given speed v and a radius r, the curve must be banked at the angle theta such that tan of theta is equal to v squared over rg. Okay, so show for speed v and radius r, theta must be such that tan theta is equal to v squared over rg, v squared over rg. So that's part A. Part B, find the angle at which the curve should be banked if a typical car rounds it at a 50-meter radius and a speed of 13.4. So the oh, goodness. That one snuck up on me. What was I saying? So this is the type of question where if you saw it on the AP exam, my advice to you would be do part B before part A. Pick up those easy points, because for part B, all you have to do is use that equation that they're asking you to prove. The proof is probably going to be more difficult, but if they're giving you the equation that you're supposed to prove, and then they're asking you to use it on some numbers, you can just go ahead and use it on some numbers. You don't need to prove it first. You can score the points for part B before doing part A. So if you're looking at, the proof and you're not even sure where to start, just go ahead and pick up those easy points, move on to another question, come back to it later. Sometimes while you're doing other questions, new ideas will pop up in your head, and that's just a more efficient use of your time. I wish I didn't have to teach test-taking strategies like that, but that's the world we live in, where everything is just a standardized test, because that's a perfect way to figure out how well people understand things. That's not hackable at all. It's totally impossible for people to pass the test without understanding the material, right? Oh, if only. I've seen people brag about how they crammed for an AP exam in the last week or so and got a 5. Don't be one of those people. Even if it's, not your number one passion, try to come out of the course having learned something. Anyway, that's enough of me ranting. Let's go ahead and do the proof part. Plugging in numbers, you know how to do that. So, in case you want to play around with part B, the numbers they gave for part B. Find theta for r equals 50 meters and v equals 13.4 meters. That's part B. You can do that on your own. It's really easy. Just plug the numbers into your calculator. But my focus is just going to be on drawing the diagram for this situation and understanding it, understanding this sort of new behavior of the normal force that we haven't seen before, and just getting some practice with a banked curve problem. And then I think I'm going to follow up with a little bit of a discussion of how friction can change things. And then I'll give you a problem or two to look at for homework, and we will start off with those next time, which, if everything goes according to plan, will be tomorrow. Hopefully tomorrow will be a Sunday that I don't have to cancel. Anyway, I'm going to draw two diagrams. So one is going to be a diagram from like bird's eye helicopter view. Just looking at the vehicle from above. I'm going to draw the vehicle so that it's over here. The centripetal force it needs would be this way. It doesn't really matter if the car is driving this way or this way. I'm going to say it's driving this way, for example. It doesn't matter if we're looking at the car from behind or in front. Speaking of, here's the other perspective that we want to draw, and the one where more of the action is going to happen. So here's the road banked at an angle theta, and here we are looking at the car. I guess if the car is moving that way, then we are looking at it from behind, so it's heading into the page. Now, what you may remember from inclined plane force problems is probably going to give you trouble here, because a lot of students will take what they learned from the force chapter with inclined planes, and that'll be kind of the source of confusion for them with how the normal force is acting here. So here, the force of gravity is not actually going to turn into components down the incline and into the incline. We're not going to have your typical mg cosine theta this way, mg sine theta that way, and then normal force canceling with mg cosine theta. And the reason for that is because the acceleration we're expecting is different. For inclined plane problems that we've done up until this point, the acceleration has always been either up the incline or down the incline, so it made sense to use forces and components that were either parallel or perpendicular to the incline, and the normal force's job was really just there to, I guess, provide friction whenever the surface was rough, or otherwise just cancel out with the gravity component that's perpendicular. But that's not happening here because the acceleration we're getting is not parallel to the incline. The acceleration that we need to get has to be that way. That's the direction of our centripetal acceleration. That has to be the direction of our net force. So the normal force has to serve a different purpose here. The normal force has to serve a different purpose here. So this time the normal force is actually going to be greater than what it would be in the more typical inclined plane case that we've seen up to this point. In this case, the normal force has two jobs. Job one is to cancel the gravitational force because, as you can see, our centripetal acceleration is completely horizontal. So vertical forces like the force of gravity, which I don't need to break into components this time, need to be canceled out. I don't need to break gravity into components because my net force needs to be in this horizontal direction, which means my other direction would just have to be the force of gravity is already on one of my axes. I'm using a more traditional coordinate system for this problem. I'm just using my usual X and Y axes this time instead of the parallel and perpendicular axes. So the normal force is actually the one that needs to be broken into components this time, and the normal force needs to have a component upward that cancels with the force of gravity, and then whatever's left, since this problem said it wants to achieve this without friction, the normal force component horizontal is going to be all of our centripetal force this time. But if friction was involved, then it would also need to be broken into components. If there was a friction here, let me draw it separately. If there was a friction force on our diagram, either down the incline or up the incline, either way, since they don't line up perfectly with my coordinate system, the friction force would also have to be broken into components just like the normal force. We might look at one of those after this, although I don't think I have one in this book. Not to my knowledge, anyway. That's okay, I can make one up. Now let me see, am I forgetting anything else? So that has to be the direction of our centripetal acceleration. That's just the direction of the tangential velocity, at least for that moment in time that we're freezing it in. And yeah, I don't think I'm forgetting anything else. So yeah, we need to have no forces in the y direction. Our net force needs to be exclusively in the x direction and straight towards the center of that circular path. So we would do normal force, let's see, where's theta? That's theta, which means this angle is theta, which means that this angle is theta. And since the normal force is perpendicular to the plane, that means this angle over here is 90 minus theta, so I'll do that in a different color, let's say green. This is 90 minus theta, is 90 minus theta, which then means that this angle over here would have to be 90 minus that. So this angle must also be theta. Just a little bit of geometry there. Okay, and since that angle is theta, then the y component of my normal force is going to be the cosine component in this case. It's going to be normal force cosine theta. So this is normal force cosine theta, which then by process of elimination means that this has to be normal force sine theta, and I don't have enough space to actually write it on my diagram here, but that's okay. So net force in the x direction is just going to be normal force sine theta, while net force in the y direction needs to be 0, needs to be normal force cosine theta minus mg. This, by the way, needs to equal mass times centripetal acceleration equals mass times v squared over r. So let's see what we can do with this. For this, I can solve for the normal force. Normal force is going to equal add mg to both sides. So normal force cosine theta equals mg, divide both sides by cosine theta, normal force equals mg over cosine theta. Okay, take this expression and plug it into the other equation. Take this and plug it in here. And that gets us mg over cosine theta for my normal force times sine theta. Oh, and I'm already seeing where the tan theta is coming from. Equals mv squared over r. The m's cancel. Sine theta over cosine theta reduces to tan theta, so we get g tan theta equals v squared over r, and divide by g, and there you go. Tan of theta equals v squared over rg. And it's done. Now, another question I can ask you is this. What if friction is still involved? What if friction is still involved? What if, instead of this, we have the same exact scenario, but now the road surface has a coefficient of friction mu? And I ask you, what is V minimum and V maximum? If road has friction coefficient mu, has friction coefficient mu, what is the maximum and what is the minimum speed that the car can have to safely turn the curve? So, same drawing and almost the same diagram. I won't redraw this. I'll just redraw this diagram and we'll just use this one for the bird's eye view. So here's our incline. And there's the banking angle. There's our vehicle, whether it's heading out of the page or into the page, it doesn't matter. We'll say into the page again, just so that we have something that agrees with this bird's eye view. It's heading in that direction, behind the page. And our diagram is going to be kind of similar to what we had before. So let me go ahead and draw my axes. And draw my raw forces. So I have normal force is going to be perpendicular to the incline and in that direction. Force of gravity is going to be straight down. And force of friction, well, that depends on whether the car is going at its maximum speed or its minimum speed. When the car is going at its maximum speed, that means if it goes any faster, it's going to swerve outward like that. So this is the V greater than V max trajectory. If V is greater than V max, there's not enough force to keep the car in the road, to keep the car from drifting outward. So, well, it drifts outward, it drifts away from the circular path. If V is less than the minimum, if the car is driving too slow, then the opposite happens. If the car isn't driving fast enough, then it'll slide down this path, and that's no good either. So V less than V minimum will result in a path like this, swerving inward. So that's the V less than V minimum scenario. It just kind of curves this way. I don't know why that didn't come out as a dotted line, but oh well. So that would be the car slipping downward. So the type of friction that we're working with in either case is static friction. In this case, we're talking about static friction. Now you might be saying, wait a minute, but the car is moving. How can it be static friction? Well, it's because the car is moving in a direction that's either into the page or out of the page. And it's not moving, at least it shouldn't be moving along the incline. It shouldn't be moving up or down the incline. So along the incline, we should have static friction that's trying to prevent it from sliding up or down, because that's what's happening when the car is swerving out of or into the circular path. It's sliding up or down this incline. So static friction is there to try and prevent that. So static friction is either going to be down the incline or up the incline, depending on which scenario is about to happen. If the car is going too slow and is about to slip inward, then that means the static friction would have to be up the incline in order to try and prevent that from happening. If the car is about to swerve outward, that means it's about to drift up the incline, so the static friction would be down the incline. So at Vmax, force friction static is going to be down the incline, down the incline, and not just at Vmax, even near Vmax. Meanwhile, at V minimum, the force of static friction has to be acting up the incline in order to prevent the car from sliding down. And then in between, I guess, in the case where no friction is needed whatsoever, so I guess this case right here, where tan of theta is equal to v squared over rg. So solve for v equals rg equals the square root of rg tan theta. At that specific speed, the static friction would have to be 0, because the normal force alone would be able to supply all the centripetal acceleration you need through its x component. So whatever that speed is, you find that anywhere above that speed, the force of static friction would be down the incline. Anywhere below that speed, the force of static friction would be pointing up the incline. Anyway, for this first diagram, I'm going to draw it pointing up the incline, just so it's not in the way of the rest of my stuff. So I'm going to draw a force of static friction up the incline like this for now. And we might not even need to draw another diagram for down the incline, because we can simply just change our equations by changing the signs of our static friction components to get the other case. That way we can save a little bit on drawing diagrams. Obviously, if you get something like this on the AP exam, you would probably draw both diagrams because they'd be asking for it. But if you don't have to, you can take that little mathematical shortcut. Anyway, we already determined before that this angle over here is going to be theta, so that we get a component of normal force cosine theta pointing in this direction. So that's normal force cosine theta. Oh, it's going to get crowded either way, isn't it? I already see the problem here. So we have normal force cosine theta that way. And then we would have normal force sine theta this way. We would have normal force sine theta this way. Now in this case, normal force cosine theta doesn't equal mg. And that's because the friction force has a vertical component that's going to interfere with that a little bit. So for the static friction force, I guess since it's parallel to the incline, this angle over here would be theta, right? It's the same angle made with the horizontal as the incline itself. So that means the static friction cosine theta would be over here. Let me draw it in a different color. Let's do blue. So there's force, static friction, cosine theta. And then upward, we have this. And yeah, I knew it. Yeah, it's getting crowded. I was trying to avoid that, but it still happened anyway. If I had chosen static friction pointing down the incline, we'd have the same problem of crowding because we'd have two forces to the left. But anyway, force of friction static sine of theta is that upward component. And now we can write equations. So we need net force Y to be 0, and that's going to be normal force cosine theta plus force friction static sine theta. Make that F a little bit bigger. And minus mg. And for net force X, that's going to have to be our centripetal force. That's going to have to be mv squared over r equals forces towards the center minus forces away. Forces to the left, that's normal force sine theta, minus forces to the right, that's force friction static cosine theta. And that's it. Okay, so this can look a little bit tricky, but it's actually not too bad. So one thing we can do, we can't solve for normal force as easily as we did over here, but it's still doable. So what we can do is we can rewrite our static friction forces as mu times the normal force, as mu static maximum times the normal force. I'm just going to call it mu for the sake of time, just to speed things up a little bit. So I'm going to take this second equation, and what color have I not used in a bit? How about you? And I'm going to rewrite this. mv squared over r is going to equal normal force sine theta minus mu normal force cosine theta. And then I can factor out the normal force from here. So if I do that, I get mv squared over r equals normal force times sine theta minus mu cosine theta. Okay, for the first equation, I'll add the mg over to the left and do something similar. So I'm going to have mg equals normal force cosine theta plus mu normal force sine theta, and then factor that out. mg equals normal force and then cosine theta plus mu sine theta. Okay, and then I could divide by sine theta minus mu cosine theta and get this complicated expression to plug in for normal force here, or I could do something easier, which is just divide the two equations by each other. So I'm going to take this equation, this one, divided by this one. So left divided by left, mv squared over r divided by mg, the m's cancel, and I'm left with v squared over r divided by g. That's just v squared over rg. Something is starting to look rather familiar. Equals, and then normal force times this stuff divided by normal force times this stuff. Wait a minute, the normal force cancels out too. So normal force over normal force is gone, and I'm just left with sine theta minus mu cosine, sine minus mu cosine theta over cosine plus mu sine, cosine theta plus mu sine of theta. And multiply this by rg and take the square root, and that is what again? That is V maximum. So that is, all right, V max squared over rg. So V max, I guess, where do I want to write it? I guess we'll write it over here. V max equals the square root of rg times sine theta minus mu cosine theta over cosine theta minus mu, or plus mu sine theta. Okay, that's V maximum. That's the upper speed limit. Now, what about V minimum? So with V minimum, the only thing that changes is the direction of the static friction force flips from this way to this way, a complete 180-degree turn. So instead of an upward and rightward component, it's going to have a downward and leftward component. Its downward component will still be its total magnitude times sine theta, and its leftward component will still be the cosine component. So really the only thing I have to change is the signs over here. The only thing I have to change is this plus turns into a minus, and this minus turns into a plus. And that means that these pluses turn into minuses, and these minuses turn into pluses. So basically I get the same result, except this is a plus and this is a minus. So V minimum will just be square root of rg times, let's see, sine mu cosine, cosine mu sine, sine mu cosine, and cosine mu sine, and then instead of a minus on top and a plus on the bottom, it's going to be a plus on top and a minus on the bottom, and that is your V minimum. And there we have it. Okay, so that leaves us with homework. What do we want to do for homework? Let me see where that problem is. Okay, here it is. So let me flip the page and draw the diagram for it, and this is what I will leave you with for today. So they actually use something that we're going to learn from the next chapter, but I'll modify it a little bit so that it's doable with what we currently know. So the problem is, in a popular amusement park ride, a rotating cylinder of radius 3 meters is set in rotation at an angular speed of 5 radians per second. I'm just going to translate that for you. It just means that the tangential speed is 15 meters per second. So V tangential is 15 meters per second, and the radius is 3 meters. And they have a drawing of it, so they've got an axis of rotation, and then they have this sort of cylindrical room elevator thing. And then there's a person drawn on the inside with their back against the wall. So it says that the rotating cylinder is set in rotation, 15 meters per second, tangentially. Then they say the floor drops away. So they're standing on something at first. The thing starts spinning, and once it starts spinning at a high enough speed, then they drop the floor from underneath the people on this ride. And yet, those people hang against the wall. The floor then drops away, leaving the riders suspended against the wall in a vertical position. What minimum coefficient of friction between a rider's clothing and the wall is needed to keep the rider from slipping? And it also has a hint. It says, recall that the magnitude of... Oh, they're just telling us how friction works. You know that friction is mu times the normal force. So, yeah, they are, if we look at them from above, the people inside this ride, so I guess this will be just a picture of somebody's head. And this, let's say this thing is rotating like that. That would mean that this person's tangential velocity at this moment would be that way. And the center of their circular path would have to be this. So they need some sort of centripetal force pointing towards the center. Whatever forces are acting on this person, the sum of those forces has to be pointing that way. That's the direction of the centripetal acceleration, and also the direction that their net force needs to be. So I would draw a force diagram here. Their back is against a wall, so figure out what force is acting on them because of that. And then they mention friction. What is the friction's job? And of course, they still have weight because they're still on Earth. So figure out how all of that factors in. That will be homework for tonight, and we'll look at it at the beginning next time, which should hopefully be tomorrow. So let me think. Any final comments? Well, the plan for tomorrow should be to just talk about gravitation, just kind of introduce the basics of it, introduce Newton's law of universal gravitation and change our understanding of the gravitational force a little bit, talk about how gravity changes when you start to get really high up in the sky, far away from Earth's surface, up to and even beyond the moon. And actually, I have this really nice problem here that, well, maybe we can save that for like a review or something. Yeah, I'll probably put that in like, maybe not next stream, but the stream after next depending on how far we get with next stream, the stream after next might be a short one in terms of new topics, and then we'll spend the rest of it doing mixed review, I'm thinking. And that's where I would want to do this one problem that can trip students up just because of the algebra and trig. I'm gonna need to remember to do that problem. I have a feeling that I'll forget it if I don't make a note of it or something. But anyway, I think that is enough from me. Hopefully you enjoyed, hopefully you learned something useful. If you have any questions, if you feel like there's something I skipped over, I certainly feel like I finished this a little too fast, but maybe it's a short topic. Or maybe my brain is just not functioning correctly today. Who knows? Could be both. But yeah, if you feel like there's anything I missed or you have any other questions, feel free to ask in the comments or ask in the stream next time, whenever that is. Hopefully tomorrow if I keep things on schedule. And I will see you next time. Have a good one.